So let's check the virtual classroom from home. Can you hear me? Do you hear? Okay. Good. Let me share the screen as well so that you get the recording of what we do. Okay. Everything looks good. Okay, so good afternoon. Today we finish what we started yesterday. We have 3 hours of lecture and then we will have 2 squads of laboratories. Some people already saw the laboratory yesterday, so today we do the same for the other people. Short summary about what we did yesterday. Yesterday we introduced the concept of machine learning and pattern recognition. We saw some tasks, in particular classification tasks. We analyzed it a bit more in detail, and then we started giving a sequence of steps that we will need to solve to obtain our classifier. We said that we would cover mainly classification as a task. This will allow us to talk also about density estimation. The other big topic that we don't cover is regression, but in some sense you have already covered it probably in other courses, even if you didn't know that it was something that is similar to what we do in machine learning. So linear regression and those kind of things, like minimum square error and those kind of fitting and similar things are techniques that are used in machine learning for regression, but that you should hopefully have seen also already in other courses. So here we will focus on classification and density estimation. Then we said that we divide our problem into 3 steps: feature extraction, that we assume, since it's task specific, is already done by somebody who knows the task. So for example, we have seen in the laboratory yesterday with those who were there, and we will see with those who do it today, that the dataset that we use for our laboratory contains features that have been extracted by somebody who knows that those features are relevant. Our task is classifying different variety of flowers. We will see for those who didn't see it yet. Somebody who knows the variety of flowers decided that the length of the petals of the flowers can be a feature that allows us to discriminate between the flowers. So we will see that one of the features that we will use is the length of the petal of each flower. So our feature vectors will contain physical quantities related to the objects that we want to classify. Which physical quantities? Those computed by some expert of the task. Then we said that typically we have large dimensional data to work with, and this can be troublesome because it can lead to overfitting. The larger the dimensionality of the data, the more complex it becomes my classifier. We will see that typically the number of parameters of a classifier will grow with the dimension of the input data. So the larger the input, the more complex is my classifier. The more higher number of parameters I have to estimate, this can result in a larger risk of what we call overfitting. We learn characteristics that are useful for discriminating classes in the training set, but that are actually artifacts that appear only in the training set images, in the training set samples. We did an example with images yesterday. So if we are able to squeeze down the size of the input, then our classifier will have less parameters, will be less free to, and therefore it will have less chance to find useless feature patterns that appears only in the training set but do not generalize to unseen data. And then we said that finally we will build our classifier, and we discussed 3 possible ways of building the classifier, and we will see that more in detail in the upcoming weeks. Other questions on this part? Okay, so we have seen the part that we will need to do to perform classification. Actually, from what we said yesterday, the whole picture that I started showing yesterday, where we took a test sample, extracted features, performed dimensionality reduction, and then classified it to compute a predicted label, would look more like something like this. We will have a training set that we will use to, well, from the training set data we will extract features, and then we will use the training set to build the models for dimensionality reduction and classification. Then the inference stage will leverage the models that we have learned from the training set. So this classification and dimensionality reduction box are actually learned. So we create models that have parameters that are learned from a training set. The training set is the data that we will use to estimate everything that needs to be estimated. While when we refer to test sample, we refer typically to the samples that we want to classify. Now, one last thing that we will analyze, we said we will analyze how to build this classifier. The other thing that is important when we do this kind of things is once we have built a classifier, we need to understand whether what we built is actually useful or not. Our classifier may be inaccurate. Our classifier may not provide good results. So we will see that we will spend some time to figure out how to evaluate the performance of a classifier. Something that we will see how to do this in a relevant way that will give us some relevant information on the quality of our classifier. Something that is already useful to say, so we say it now, even if we don't see yet how we practically measure the quality of our predictions, is that to perform evaluation, it's important that evaluation should give us a metric that tells us how the classifier would work when we actually apply it to the data that we want to classify. We already said yesterday, in case of overfitting, we may have a classifier that does very well on the training set, but then when applied on data that was not used for training, it will perform quite worse. So our evaluation, if we want an evaluation to be fair, to give us some useful information, it should mimic the use case. So it should be done on data that was not used for training. So we should evaluate the classifier on data that is as similar as possible as the data that we will use the classifier on. Of course, we can't evaluate on data that we have yet to see our classifier, because if we don't have the data, we can't evaluate that. So what we do is we simulate applying the classifier to a real task. How? We use a set that is again labeled, which is called typically evaluation or test set, that contains samples which are not really unknown, in the sense that this is again a labeled dataset. We know the actual label of the samples in this dataset. This is in contrast with the real use of the classifier. We want to use the classifier on data for which we don't know the label, because if we knew the label, there would be no reason to use our classifier at all. But here we simulate using the classifier on data that is unlabeled, but using a labeled dataset. Why? Because this will allow us to evaluate whether our labels predictions are good. The important thing is that this evaluation set should be a set that mimics unseen data. What does it mean? It means that the dataset, first of all, should have not been used to make any inference on the model. So any decision we make on the model should not depend on the data that is in the evaluation set. What does it mean? Well, It means that, of course, the evaluation set should not use any data that was used to train the model, but it also means that ideally it should not be used to make any decision. What does it mean, any decision? It means that the evaluation dataset to be a real estimate of how our model will perform should not be used to decide anything, not even which classifier should I use for my data. In the moment I use the evaluation set to make any decision, that is not an unbiased evaluation anymore. Now, this poses some problems that we'll see in a moment. Other thing that is important, since this should mimic our application, so the real usage of our system, this evaluation data should be as close as possible to the data that we want to classify. Now, why this is important? This is true also for training data. The better the training data mimics the real use case, the better our model will be. But this is even more important for the evaluation data, because the evaluation data is what we use to decide whether our classifier works or not. So if it doesn't mimic the real application data, then we may end up thinking that something works when it doesn't, or vice versa. We may throw away something that looks like it doesn't work, while maybe it was actually good for our problem. Now, where is the issue? Is that this is fairly easy in the sense that if we just don't estimate model parameters from the evaluation data, then it's easy to avoid having biased results because evaluation data was used for training. The second part is a bit more difficult. I said to be completely unbiased, my evaluation set should not be used to make any decision on the system, not even which model or which preprocessing or which data I should use to train my system. Every time I make a decision by saying, okay, if I do this, then my evaluation results will improve, that is already a decision made using the evaluation data. So, for example, imagine you have trained two classifiers, you evaluate on the evaluation data, and you have some accuracy for the two classifiers. Then you find that the first classifier is better than the second one, and you decide that you will use classifier 1. In that sense, you are already using the evaluation data to make a decision, because you decided to use classifier 1 instead of classifier 2. Now you can understand that this is has a much lower impact than actually using the evaluation data to learn the model parameters, because I'm using it to make a decision where the evaluation data impact on my decision is smaller. I'm saying I'm learning less information than if I was using the evaluation data directly to train the model. But in any case, from now on, whenever I will use my evaluation data to make assessments, this will be biased because I will have chosen the classifier based on the optimal performance on the evaluation data themselves. Problem is, the second step is ideally, because in practice it cannot be avoided. To avoid this, we would need to have a new evaluation set every time we want to evaluate our system. And this is typically unreasonable. It would also pose the problem that since evaluation sets are limited, so they have a finite number of samples. Even if we take two different evaluation sets from the same population, we may end up measuring different values for our metric, because essentially our metric will measure an average of the number of errors, but if you have a finite number of samples, the average can change depending on the actual samples that you have in your dataset. Which means that in practice, evaluation or test sets are often employed to compare the performance of different systems, but we should try to avoid as much as possible basing our decisions on the evaluation set. It's to say, the more I use an evaluation set, even just to compare different systems, the more I may end up with biased results that do not generalize to additional data. So I need to pay attention to this. Now, where does this become a problem? It becomes a problem when we have models that have what are called hyperparameters. What are hyperparameters? Well, we said up to now that we build models which contain parameters, and then that learning means that we go from the data to an estimate of the parameters that we will use then for inference. For example, we said if we want to build a density model for some set of points, we can decide we model the points as a Gaussian distribution, and then our parameters are the mean and the variance. Then we can estimate the mean and the variance of the training set and use those as the parameters of the distribution that describe our data. Now we will see, and we will see already today, that there are some models which depend on a set of parameters that cannot be directly learned using this paradigm. In the sense that, well, they do not behave as the model parameters themselves. Why? Because we will see that the way we learn the model parameters, we said, is through the definition of an objective function that we will optimize. So learning will correspond to optimization of an objective function. But we will see that this objective function, when expressed as a function of these hyperparameters, will typically have minimum in respect to the hyperparameters that are trivial solutions that are of no interest. That is, optimizing the objective with respect to the parameters will lead to meaningful conclusions, but if we were to optimize the function with respect to the hyperparameters, they would be essentially useless in terms of the task that we want to solve. To make an example, we still didn't discuss it, but we said yesterday one of the problems is dimensionality reduction. Dimensionality reduction, we said we have a input space that is very large, and we want to map this data through a function, this is x and this is y, that is of much smaller dimension. Now, we will have a function that is actually a parametric function. So we will see that we will use functions that depend on parameters. One way will be we will optimize this function to optimize some criterion. Now, what is a hyperparameter of the model? A hyperparameter of the model is the size of the output space. Now, we will see that one of the methods that we will use to estimate the function will be, we will try to figure out a mapping such that we will actually estimate two mappings, forward and reverse, and we will try to estimate jointly these two mappings in a way that allows us to minimize the error that we make due to the reduction. What does it mean? It means that we will have a large dimensional data, a function that maps it to a small dimensional data. Then we will figure out a way to rebuild as much as possible the original vector, and then we will try to minimize the difference between the original input and the reconstruction that we make from the small vector. Now, what is a hyperparameter? We said it's the size of this space. If our goal is to minimize the loss of information, so we want to be able to reconstruct as much as possible the original data. Imagine when you do compression with a zip file, you reduce the dimensionality, but you want to preserve all the information because you want the bits of your original data to be all reconstructible. You want to be able to reconstruct the original files when you compress. So the size of the space is a parameter that we can tune. And depending on the size of the space, we may end up with solutions where we can reconstruct the original data in an easier way, or the smaller is the subspace, the harder it will come to reconstruct the original data. Now, if we use as our goal that we want to find a model where we compress information and then we decompress it in a way that the decompressed version is as close as possible as the original information, then a trivial solution is to set m equal to n. If we set m equal to n, we have a subspace that actually has the same size as the input space. The f function becomes the identity function, so it just takes my x and returns x, and I have dimensionality reduction techniques that achieve the best possible reconstruction. I minimize the reconstruction error as much as possible. My reconstruction will always be exactly my input, but in terms of dimensionality reduction, this is useless because I'm not reducing the dimension at all. So if I cast my problem as finding a transformation such that when I compress and decompress my data, I get the decompression that is as close as possible as the original data. If I optimize this with respect to the size of the intermediate space, the one where I reduce, then I get the trivial solution. I can minimize my reconstruction error by simply setting dimensionality of the reduced space equal to dimensionality of the original space. So I have the trivial solution. If I want to minimize my reconstruction error, just don't compress anything and you will not have any error in your decompression. If you don't change your input, then you can reconstruct your input perfectly. But this is obviously something that is not good. So we need to figure out a way to find a good value for the reduced dimension space. It is, we need to find how much we can afford to compress and how to evaluate what is a good value for our compression. Another case where we have something that is not a hyperparameter, but we have a similar problem, we have competing models and we want to decide which one to use. For example, we will see today, we said dimensionality reduction can be used to simplify classification, but the amount of dimensionality reduction that I apply may influence how good the classifier is. So should I apply it? Should I skip it because the classifier is good enough and dimensionality reduction will just throw away useful information? All these questions require a way to decide whether which kind of pipeline I should take. Should I, as I said, apply dimensionality reduction or not? Should I use one classifier instead of the other? And so on. Now, all these things go under the name of model selection. We need to decide which model or which combinations of models we want to use as the best one. All these, if you want, also hyperparameter tuning goes under the terms of model selection. You can imagine that hyperparameters essentially define different models. The size of the reduced space in a dimensionality reduction approach leads to different models. You can imagine that each model is parameterized by the size of the reduced space. We need to be able to select among competing models which one we want to use. We have said we cannot use the training data directly in the same way as we do for the standard parameters because we can't directly optimize. And I say directly, that means with the same objective function, we can't estimate both the parameters and these hyperparameters. We cannot also use the test data because if we optimize the hyperparameters using the evaluation data, that will lead to biased conclusion. We'll find the solution that is best for that specific dataset, but that's not necessarily true for a different dataset. So to solve this problem, we introduce a third set that we call validation set. The validation set is part of the training material and it's something in between. It's a set, it's part of the training set that I will use as if it was an evaluation set. But I will use it to make decisions, so it's in all effects part of the training set. How? We take our original training set and we can imagine we partition it into two parts. The first part, we call it here model training data, just to remember that this is the data that we will use to train the model parameters. So from here I will infer the model parameters, and then I will have a subset of the original training data that I will call validation set that I use to make decisions on the value of hyperparameters. How? Well, essentially, I will train my model with using different values of the hyperparameters. I will, for each trained model, each of these will give me one different model. Then I will take these different models, I will evaluate them on the validation data. So I will treat the validation data as if it was an evaluation set. But I will use this validation data to decide which model is the best. So which one of those three values for M, for example, I should use. So this is a sort of evaluation set that is used for training. What does it mean? It means that it gives me a way to estimate the value of the model parameters. It also tells me that just measuring the quality of my classifier on that data may lead to biased conclusions. So if then I want to see how well really the data, the model would be for unseen data, I would need an additional evaluation set. Why it can be biased? Well, because the same thing that happens when I estimate model parameters can happen when I use the validation data to perform hyperparameter selection. I can overfit the validation data. I can find a solution for the hyperparameters that works well for validation data because I'm looking for the solution that is best on those data, but the best on those data may not necessarily be based on something that is general to the characteristics of the evaluation data that I want to classify. It's the same problem as overfitting. My good results may be due to some effects that are present only in the validation data. So it's typically less evident. That is, the number of hyperparameters that we estimate is typically small. So the risk of overfitting the validation data is much smaller than the risk of overfitting the training data when estimating the standard parameters. But still, there is this risk, and for this reason, the validation data can be used to make decisions, but cannot be directly used as a prediction of how well our model will work on real unseen data. Validation data does not unseen data anymore because it was used to learn some part of the model, the hyperparameters. So essentially, this part will be used to learn the model parameters. This part will be used to learn the hyperparameters. Then this maybe we will discuss later near the end of the course. Okay, questions on this? Okay, if there are no questions, we can start with the first machine learning algorithm that covers dimensionality reduction. So what we said up to now, we will now put it in practice. So let's go back to dimensionality reduction task. We want to take our input that is typically large dimensional, and we want to map it to a small dimensional space. So we want to map it to a, here is n this one and n this one, to a small dimensional space. For what reasons? Well, we have discussed it already yesterday. This is the same slide, if I remember right, more or less what you already saw. Compressing information. As I said, dimensionality reduction, you can see it as a possible way to perform compression, similar to what you have with zip files, similar to what you have with JPEG, similar to what you have with MP3. The only difference here is that the input and output space have a fixed dimensionality, while for your MP3 audio, you have input space that whose size depends on the length of the audio, and the output depends on the compression rate. So the output is not fixed dimensionality, but the idea here is the same. if I can represent a vector of 2 million data with 100 parameters, then I can compress the information and store it with much less memory required to store it. We have seen another reason we may want to reduce the dimensionality, to remove what is called unwanted variability. We made an example yesterday. If our inputs are images of people and we want to recognize whoever is inside, we can imagine that the background parts of the pictures are useless. So if we represent the pictures as arrays, each component of the array will correspond to 1 pixel of the image. If we are able to identify which pixels are background in all images, we can just throw them away and avoid that the classifier may extract from those pixel information that is actually an artifact that leads to overfitting. For example, all pictures of Alice show blue sky because they were taken in the sun, or picture of Bob were taken under the rain, so the sky is gray. Then we decide that the sky gray means that the picture is from Bob, which is not true, of course. So this remove unwanted variability is connected to simplify classification. We also said that simplified classification means also that if we have lower dimensional data, then it's easier to estimate distributions in space, because the larger the input dimension, the more sparse the data. The number of elements that falls in a box of size 1, or if you want, we have seen this yesterday with a histogram. If I want to use a histogram to represent high dimensional data and I want the same number of steps over each axis, if I want k steps on each axis, I need k to the power n voxels if my space has a dimensionality of n. So if I want to map all the possible space and compute a histogram in an n-dimensional space, I need to use k to the power n voxels, which means that typically all the bins, which corresponds to the bins of an histogram, all the bins would essentially be empty in a high-dimensional space. And then the last task that we will not really use much, because the methods that we see are not particularly suited for this, but still it's something related to dimensionality reduction. There are better methods than what we see, but we don't have time to discuss those. But in any case, it's visualizing data. We can't plot samples that are few millions of components, but if there are 2 or 3 components, we can plot them and look at them. So if we are able to map some data set to a small dimension, where the small means that it's small enough for us to visualize, then we may be able to do some plots that give us some intuition on how the samples are distributed, and therefore how we should approach our task, whether it's a classification or just dimensionality reduction or anything else. The more I can see about my data, the more I can reason on what I need, what may be a good way to deal with the data. The less I can visualize about the data, the more I have to rely on intuition to decide what to do. Now, all these goals are actually different, so there is not going to be some solution that works for everything. The solution that we will use depends on what we want to do. And what we want to do, that means that we need to define exactly what we want to do. We need to measure, to decide how we can measure whether our algorithm is actually achieving that. And then once we have defined that, we can try to figure out a solution to optimize our goal. What does it mean? It means that, for example, if we want to compress information, we said before, we have our input, let's call it X. Then this gets mapped to a small dimensional space, let's call it Y, and this is M. Then if my goal is to compress information as to preserve as much information I had originally, I can imagine that I may want to be able to invert the process, so to go back from the reduced data to the original data, now this may not be a lossless process. I may lose some information, but I may think that a good way to measure how well I reconstruct I compress my information is the better I can reconstruct my original data, the better is my compression algorithm. If with the same number of bits, so with the same dimensions of the subspace, I can reconstruct in a better way the input data, then I got a better algorithm for compression. Now, we need to define what it means, retain maximum amount of information. Here, I'm giving you already a hint of what we will do. We will measure error rate in terms of distances, but depending on the task, it may differ. When you do audio compression, the way you measure the information that is retained is based on acoustic property, not just of the signal, but of the human ear that will listen to that recording. So we know that the human ear can filters out some frequencies, you know that it has some response to some audio. So the compression algorithm will take all these things into account to reconstruct an audio that, from the signal point of view, may not look like the original audio, but when listened to by a human, will sound like the original audio. So these algorithms are led by the definition that we use for reconstruction error. The way we define reconstruction error will define how we achieve a good compression. Other tasks that we may want to solve, we said we want to use dimensionality reduction as a way to simplify classification, which means that our goal is to find a reduced representation which can be easily classified. For example, imagine I have two class problems where these are the points of class 1 and these are the points of class 2. Now you can imagine that this is a two-dimensional space. Imagine that I want it to be reduced. To reduce a two-dimensional space, I need to map it to a one-dimensional space. What does it mean to map it to one-dimensional space? I want to represent each of these samples by a single number. A way to do that is to project this data over a direction. If we project the data over a direction, then each sample can be represented by the coordinate of the corresponding projection on the projection line. So we map these samples to these positions. We map the green samples to these other positions. Then the coordinates of each point is a number, so it's a value that lives in one-dimensional space that represents a reduced version of the original data. Now, if my goal is to increase classification, then I can imagine that choosing a direction like this will not be as good as choosing a direction like this. In the first case, what happens if I project my samples? What happens is that the green projections will overlap a lot with the red one on this vertical line. If I were to project on the horizontal line, then the projection of the samples would be well separated. If I have to perform classification on this data, I can just say whatever is on the right of this point looks like it belongs to class green. Whatever is on the left, it looks like it belongs to class red. So the way I choose the direction in this case may be to preserve what is called discriminant information. That is, we look for a direction in this case that contains information that is useful to discriminate the classes. Not that this information was already in the original data. When I do this kind of processing, it's as if I were cutting the original two-dimensional space with this plane. We will see this in detail. But I'm here doing the mapping where I throw away directions which do not give me the information that allows me to separate the classes. Over this direction, there is little information that can be used to separate these two classes, and they keep only a representation that is small dimensional, but contains the discriminant information that I'm interested in. So it preserves discriminant information in a more compact representation. Then, if I want to do data visualization, as I said, I may want something that is tailored to mapping points to two-dimensional or three-dimensional space. And in this case, I may be interested in something that preserves as much as possible the relationship within the data. What does it mean? It means that in this case, my function may be very complex, but it may be a function that allows me to take input pictures, and then the output are two-dimensional samples where pictures of the same person are close by, while pictures of different people are far. So these are pictures of, let's say, Bob, Alice, and then this Charlie. So I may want to find some mapping from the input space of images to a two-dimensional space where the mapping essentially preserves the similarities between pictures. In this case, the similarity defined as similarities on the person that is depicted in the picture. Of course, this may be as easy or as difficult as the task, as the characteristics that I want to preserve, the relationship that I want to preserve. Now, for this last part, we will not see specific algorithms because we don't have time to do everything, but we will see a way to solve these two problems. And of course, up to some point, they can be used also to perform visualization, because they can, in any case, be used to plot, to do map points to two or three-dimensional space. So in some cases, they are good enough. So the two techniques that we will discuss are principal component analysis, which essentially will be akin to preserve maximum amount of information, and we will see it's an unsupervised classifier. Here you're seeing that we never defined a classification task. We just defined we want to preserve information in the data. We didn't specify that this information is related to a concept of class, and indeed PCA will be unsupervised. And the second one is called linear discriminant analysis, which addresses the second problem. So this time it's supervised, because to know what is discriminant, we need to know the labels of the classes, because we need to know. We want a direction that allows to separate the classes, so it's not just a direction of the space, but it's a direction that should take into account the classes of our problem. So this will be supervised, and both will be linear methods. What does it mean, linear methods? That our mapping function will look something like, if we want to map to one direction, it will be a projection over a vector, and for multiple directions, it will be a linear transformation where we essentially, we will use the word projection, even if for LDA it's not simply a projection, it's something slightly more complex, but the overall goal we will see is not different. So I may use the word projection even if it's not 100% correct wording for LDA, but in any case, it's a linear transformation of the data where this linear mapping will be a real projection for PCA and something more, a more general linear transformation for LDA. In this sense, these are linear methods, because this is taking a vector and multiplying it by a matrix, it's a linear operator. Matrix multiplication by A, it's a linear operator. Okay, I think we can stop here for a moment. So let's make 10 minutes break now. Okay, so we said we are going to discuss two linear methods. This will require us to make use of some linear algebra results. Here you have a reference text on the results that we will use on properties of matrices. This doesn't contain proof, it just contains results. I hope it's still online because I didn't check. It contains lots of results on properties of matrices. So, for example, properties of trace, determinant, derivatives, and so on, much more than we will actually need. It's a reference if you need to recover some of the results that we use. It doesn't give you proofs, so it's just a collection of, or maybe it's mainly a collection of results, but it's there as a reference. Now we will mainly use a very limited subset of these, but just in case, that's a good reference should you ever want lots of properties of matrices in a single place. You can find them there. Now I will, before we start seeing PCA, short recall of some of the concepts that we will use. I hope you are still fresh, but I'm sure that you are not, on eigenvectors and eigenvalues. So who does not remember eigenvectors and eigenvalues? Okay, who does remember them? Okay, so the majority does not. So go back to your first year books and revise eigenvectors and eigenvalues, at least the definitions. Eigenvector is, if we have a matrix A, we have a right eigenvector is a vector that satisfies this equation. So when I apply A as a linear transformation to X, then what I get is a scaled version of X. L is called eigenvalue. Sorry, lambda is called eigenvalue, and X is called eigenvector. Actually, in this case, right eigenvector because it solves the problem on the right. If it solves the problem on the left, this is called left eigenvector. Now, if we have a square symmetric matrix, what is a symmetric matrix? What is a symmetric matrix? A symmetric matrix is a matrix which has the same elements across the diagonal which are the same. So if I have 3 here, I have 3 here. If I have 4 here, I have 4 here. If I have -1 here, then I have -1 here. So essentially, the transpose of A is equal to the matrix itself, symmetric matrix. Okay? If I have a symmetric matrix, I can decompose it in the product of 3 matrices in this way. I can decompose the matrix even if it's not square and symmetric, but if it's a square real symmetric matrix, I can decompose it in this special way, where I have a matrix V that is a real matrix whose columns are orthogonal, so it's an n times n matrix, so the matrix is orthogonal. What does it mean, orthogonal matrix? It means that the matrix times the matrix transpose is the identity, which means that the transpose of the matrix, sorry, the opposite. The inverse of the matrix is its transpose, which means that if I take 2 columns of this matrix, what happens? What happens is that V1 transpose V1, which is nothing else than the scalar product of the column V1 with itself, is 1. And then if I have any 2 If I take any two columns and I compute their product, then it is 1 if I is equal to j, otherwise it's 0. So I have vectors that form a basis of a space. They are orthogonal among each other. Each of them has length 1. The product, the outer product of, sorry, the scalar product of one of the vector with any other one, any other, is 0. With itself, it's 1. V is a matrix that is orthogonal that contains on its column the eigenvectors, or right, but right in parentheses because this is symmetric, so we don't need to distinguish between right and left eigenvectors, so it contains the eigenvectors of matrix A. And sigma is a diagonal matrix. We saw last week what is a diagonal matrix. Is a matrix which has all elements on the diagonal, which may also be 0, but may be different than 0, while all the rest of the matrix is 0. So all elements outside of the diagonal are actually 0. So we have a diagonal matrix. And what are the values of sigma? They are the eigenvalues of A. So I have a matrix where each column V is an eigenvector of A, and each element of sigma is an eigenvalue of A. And how they are arranged? Well, if Vj is the jth eigenvector of A, then sigma j, the same element, the element in the corresponding position on the diagonal matrix, is the corresponding eigenvector. That means that A transpose Vj, A Vj is equal to sigma j Vj. So it follows, it holds this. This is what is contained in those matrices. With V being orthogonal, so the inverse of V is equal to the transpose of V. Now this holds for a symmetric real square matrix. For a general non-square matrix, we will use a, I wouldn't say generalization, but a different decomposition that is similar to the eigenvalue decomposition, in the sense that for real square symmetric matrix, the two will be essentially, well, the eigenvector decomposition corresponds to a singular value decomposition for a real symmetric matrix, but of course it's not the same does not apply if the matrix is not square, like in this case. A singular value decomposition is defined for any rectangular real matrix A, and it tells me that I can represent matrix A as the product of 3 real matrices, which contain what? Well, the first is a matrix U that is a square orthogonal matrix that contains the eigenvectors of A transpose. V is an orthogonal matrix that contains the eigenvectors of A transpose A, and sigma is a what is called diagonal rectangular matrix. Now we will see what it means to have a matrix that is both rectangular and diagonal in a moment, that contains what are called the singular values of A. Both U and V are orthogonal, and sigma is rectangular diagonal. What does it mean? It means that if A is a tall matrix, let's say, so number of rows larger than the number of columns, then we will have a U matrix that is always n times n, a V matrix that is m times m, and sigma will look like this. So I will have a n times n diagonal matrix on top, and then followed by all rows that are 0. If I have a wide matrix, then it will look like this. Again, this is n times m, m times m, and sigma is rectangular diagonal. What does it mean? Again, n times n matrix, and the remaining columns in this case will be 0. So I have elements different from 0 only on the main diagonal. Now we won't prove that this exists for every matrix, but this kind of decomposition exists for any matrix. It's actually non-unique. Typically, we assume that these values are sorted in decreasing order. The decomposition is not unique, but there exists a decomposition for any matrix that can be expressed in that way. And we will use these results in a moment. This is a generalization of the eigenvector decomposition, because you can see that if A is square symmetric, then U sigma U transpose is a decomposition that meets these properties. So it looks like a singular value decomposition. So it generalizes in this sense the eigenvalue decomposition to any square real, any non-square real matrix. Now, the second thing that we will need is, and we will use this property to actually compute the solutions in the next lab for the PCA. The second thing that we need to recall is what it means to project a point over a direction. Before the break, we said that our linear methods will look for directions and will behave like linear transformations. What does it mean? It means that the methods we are going to study compute, well, in the case of PCA and in the case of LDA, it's slightly similar, but we will see the difference when we get there. In the case of PCA, what we do is we transform our data by projecting the data into a smaller subspace. So we take our input samples and we project them into a smaller space. What does it mean to project a sample in a subspace? We start defining what it means to project a point over one direction, and then we generalize it to several directions. First of all, we represent a direction with a unit vector. That is a vector that has unit norm. The norm of u is 1. A vector that has a unit norm represents a direction in which way, well, we can imagine that we consider the axis that is pointed to by the arrow associated to the vector. So we consider the vector as an arrow that starts from the origin and then ends at the coordinates, in this case, square root of 2, looks like. So this vector u is a unitary vector that represents the direction that points from the origin towards this point. It behaves like it's a unit vector, so it represents the direction. This direction behaves like an axis of a coordinate system. So it's by itself, U defines a one-dimensional coordinate system that corresponds to the axis defined by the direction of U. Now, I said direction. To be more precise, the direction is the line over which U lies, and then the side towards where U points is actually called the orientation. So the full thing is we have a direction which we define both a direction and an orientation for our axis. Notice that the same direction can be defined by the vector U prime that points in the opposite direction. So every direction can be defined at least with two different vectors which differ in terms of their respective sign. So the sign defines the orientation, while the line over which the vector lies defines the direction. Sometimes I will just use the word direction to mean both the direction and the orientation when it's not important to distinguish the two. Now, what does it mean to project over the axis defined by u? Well, it means to compute the coordinate of a sample over that axis. How do we do it? Mathematically, the projection of x over a direction u is computed as the scalar product between u and x. This is how you probably have been used to write scalar products. We will always use here the matrix multiplication representation, so it's vector u transpose times x corresponds exactly to the scalar product. Imagine that you have vector u, the components u1, u2, and u3, vector x. Remember, all these, if I don't say otherwise, are column vectors. ux is u1 x1 plus u2 x2 plus u3 x3. U transpose x is what? Well, I take u, I take x, matrix multiplication. This I have only one element, so I do this element times this element, so u1 x1, plus this times this, u2 x2, plus this times this, so u3 x3. So it's exactly the same. So we will use this notation. If these are two column vectors, u and x, this represents exactly the scalar product. Why we do this? Because when we generalize u to a matrix, then we don't have the bracket notation, we only have the matrix multiplication notation. So it's pointless to use two different notations for when u is just one axis or when u will define actually an entire subspace. So the projection of x over u is the scalar product and corresponds to what? Corresponds to the coordinate of x over the axis defined by u. If you imagine that you have a coordinate system where one axis is defined by u, then u transpose x corresponds to the coordinate over this new axis of the projection. So if now I take this plot, I just redraw u as an axis, then this would be the projection, would be the coordinates, so u transpose x would be the coordinate of my projection over this axis. So this small y that we will use as the representation of the projected point is the coordinate of the projection of x in the original space, in the direction over the axis defined by direction vector u. Now the second thing that I want to do, that I will need, is to express the same point in the original space, because we will need this to compute our error. What are the coordinates of this projected point expressed not as a coordinate over the axis u, but in the original space? Well, this point, if, remember that this is a unit vector, u transpose x is the coordinate of this point on this axis, then to get to this point in the original space, what do I have to do? I have to take vector u a number of times equal to my coordinate y. U multiplied by the value of the coordinate y of this point over the direction u will give me what? Will give me a vector that corresponds exactly to the point, the projected point represented in the original coordinate space. So if we want to compute the coordinates of the projected point in the original space, so in the two-dimensional space in this case, the projection of x over this line will have a coordinate that will look like u transpose x, which is a scalar, times u itself. This will be the coordinates of that x hat point. Of course, all this works if u is a unit vector. If it's not a unit vector, then you will need to scale you will need to do some scaling. That's why we use unit vectors. So this x hat is the representation of our projection in the original frame, in the original space. Questions on this? Is it clear or not? No. Okay, let's see it again quickly. I want to compute the coordinates of these projected points, and I want to express them in two ways. As coordinates over an axis defined by this vector u, and then as coordinates of the projected point in the original space. So I want to know both. If I were to look just as this axis, this is the origin, this is u, where would be x hat located on this axis? And then this point in the original space, where it lies in the two-dimensional space? Well, for the first question, the answer is, if I want to get the coordinate of x over this axis, I need to compute the projection of x over the axis, which corresponds to the scalar product. The scalar product gives me exactly if u is a unit vector, gives me exactly the length of this segment. The length of this segment corresponds to the coordinate of the projected point over the line defined by vector u. Now, if I have the coordinate of u over this axis, how do I recover the position of the transformed point? Well, to get here, what do I have to do? Well, if I look at it from the point of u, if this is a unit vector, this on the axis u corresponds to coordinate 1, 2, 3, where the vector u ends. And here I have my x hat. So how do I get to x hat following direction u? I take direction u and I multiply it by what? The size of this segment. Direction u has a size 1, so to reach the point x, I need to multiply that vector by a number that is equal to the length of this segment. But the length of this segment is nothing else than the projection, the coordinate of x in the coordinate of the projected point over direction u. So I take u and I multiply by u transpose x, or if you prefer, since this is a scalar, I can write my u on the other side. This corresponds to what? Well, I take my u a number of times as necessary to reach this point. But then what do I have? If I consider the vector as an arrow, I get this arrow. If I consider the vector as the coordinate of the points where the arrow ends, that's exactly the projected point expressed in the original space. So this corresponds to the coordinate of the sample in the projected sample in the original space. This gives me the projection over u, and this gives me the coordinate of this projection in the original space. Now, if we want to project over a subspace, then we will need to project a point over multiple dimensions. A projection over a subspace is defined how? Well, we introduce matrix U that contains column vectors that are all unit vectors, and we say more. These column vectors of U form a basis of the space where we want to project. So they form a set of coordinate axes that represents the space over which we want to project. For example, if we have a three-dimensional space, we may have basis vectors that look like this. This corresponds to what? This corresponds to the coordinate axis that will give me the projection plane corresponding to the xz plane. So these two vectors would be the basis of a plane that corresponds to the xz plane. These are the unit vector that contains the Cartesian the basis that represent the axis, the Cartesian axis of that describe the subspace. These vectors represent the directions of the axis of the space where I want to project my points. What are the properties of this vector? Well, if U contains a basis of the space where we want to project our samples, then we have that these vectors have norm 1 and they are orthogonal. So whenever I multiply the scalar product between two of them, I will get 0. That represents a set of a Cartesian axis of the subspace. So they are orthogonal one to each other. Now, how do I generalize my projection from a space, a generic space, to a subspace defined by U? Well, here in the example, it's not really a subspace because we go from a two-dimensional to a two-dimensional space. Why? Just for drawing reasons. Showing it from 3D to 2D would be much more difficult. And if I want to go, I have an initial subspace that is two-dimensional, then if I want to reduce, I can either go to one dimension or not reduce at all and stay in 2 dimensions. So the reason why the size here goes actually from, it's not really doing a reduction of the dimensionality, it's just for drawing reasons, but the idea is the same. In this case, it will not be really a projection because we are not losing information. But the idea is the same, and we will try to give an intuition from 3D to 2D afterwards. In any case, U defines the basis of the space where I want to project my point. In this case, I have two vectors, U1 and U2, which corresponds to these two directions. And you see that they are orthogonal. What does it mean to project the sample in this subspace? To project the sample in this subspace means that I want to compute the coordinate of the projection in the space defined by the basis vector. In this case, the projection will lie exactly where the original point is because we are going from 2 dimensions to 2 dimensions. But let's try to see it, and then here, and then we will try to see how it would work from 3D to 2D. In this case, I want to compute the coordinate of x expressed in the space defined by U1 and U2. How do I do that? Well, I compute the projection of U1 over the first vector. It will give me this coordinate over x over U1. Then I compute the projection of x over the second vector. It will give me the coordinate of the projection over U2. This 2 represents the coordinate of x, in this case of the real x, because we are going from 2 to 2 dimensions. So we're just making a change of the basis of our representation. If it was a projection, then this would not correspond to the original point anymore. In any case, these correspond to the coordinates of the sample represented in the frame U1, U2. So if I were to draw the Cartesian plot using U1 and U2 as axis, so now I do the same drawing, but I use U1 and U2 as axis, then my x point would be somewhere here. This would be the point with coordinates U1 transpose x, U2 transpose x. So this will be the coordinates of the original x in the frame defined by U1 and U2. Notice also that if I overlap, if I overlap U1 and U2 with the original axis, so if I redraw this second plot on top of the original one by aligning U1 with the original one, my point would end up here. If I were to do it for several points, it would look like as if I was rotating my original space. So in this case, it's behave what we will see that again when we need this. In any case, these are the coordinates of x expressed in the frame defined by matrix U. Now I can build my reconstruction. How? Well, if I have the coordinates of the points defined in this reference frame, so U1 transpose x and U2 transpose x, we call this y1 and y2. So y1 is the coordinate over this axis and y2 is the coordinate over this axis of x. If I want to represent x in the original space, how can I do that? Well, the point 8 is obtained how? I need to take first a vector that is, how do I obtain x? X can be seen as the sum of what? This red vector that I'm drawing now, which ends in y1, plus this vector that I'm drawing, let's draw it in green, here, that ends in y2. If I take these two vectors as arrows and I apply the sum of the vectors, I apply the parallelogram rule, I end up that the sum of these two vectors is exactly the position of x. So if I want to represent x starting from y1 and y2 in the original space, I just need to first represent this projection in the original space. But this point here in the original space is what? It's y1 times u1. To get here in the original frame, what do I have to do? I have to take y1 and multiply it by the length of this segment. The length of this segment is exactly the projection of x over this line, since u1 is a unit vector. And for the green vector, I do what? Well, I take u2 and I must scale it by the size, the length of this vector. The length of this vector is exactly y2. And then rule, I sum these together. This corresponds to x expressed in the original frame. I put a hat here because in general, if the projection is a lower dimensional version of the original space, then this projection will be the coordinates of the projected point in the original space, exactly as it was happening in the previous slide. In this case, since the two spaces have the same dimensionality, x hat will actually be equal to x. But if you remember here, my projection was not the same point as the original one. You can imagine if this was a 3D plot, you can imagine that my original x was somewhere here, so exactly vertical with respect to the black point. Then my original point would be here, my projection would lie on the screen surface, but my original point would still be here. So all this would be the difference between, this space would be the difference between the original point and the projection that would lie on the screen surface, okay? This if I were to go from a 3D space to a 2D dimensional space. If I have 3-dimensional space where I have a point that is not the black one, but it's actually here, my projection, this x here would actually be the projection of my black point on the screen surface. Whatever I wrote would be the reconstruction of x in the original space, but it will not coincide with the original point. My reconstruction will still lie in the space of the screen, while my point is somewhere along the z-axis, far from the screen. Now, if we express everything in matrix form, we can see that the coordinates of the projected point can be expressed as u transpose x. Remember that u contains, in this case, u1 and u2. So u transpose is u1 transpose, u2 transpose. And when I multiply this by x, I multiply each row of the matrix by the column vector x. So this will be u1 transpose x. And this will be u2 transpose x, exactly what I need to compute. And then this one is y1, u1 plus y2, u2. This we can represent as y as u, y. Why? Because I have, sorry, u1 and u2. If I have scalar values y1 and y2 and I do the matrix vector multiplication, my solution will be what? We have seen that if you can do it by hand with the rules, but if you do it by hand with the rules, you will realize that the result corresponds to taking this column u1 multiplied by 1 and then adding column u2 multiplied by y2. So when we do matrix multiplications, when we have matrix vector multiplication, we can either see it as a set of scalar products of the row of the matrix with the vector. So first row, scalar product with the vector, then second row, scalar product with the vector, and so on. Or we can see it as the sum of multiple vectors that are obtained by taking the first column scaled by the first component of the vector plus the second column scaled by the second component of the vector, and so on. It's just a matter of how we rewrite the summations and how we rewrite the components of the vector. But if you don't trust it, you can rewrite what is the definition of these products, compute it element by element. You will see that you get exactly the same result. So we can express our reconstruction in this way, which, expressed in terms of the original sample, says that if we have x, then u transpose x is the projected point, while u transpose x is the reconstruction of the projected point. So the reconstruction, what it means, reconstruction, it means the projected point is the projection of x expressed in the coordinate system defined by the basis matrix U, while the reconstruction corresponds to the same point but expressed in the original reference frame, so that it can directly be compared with the original sample x, because they are expressed in the same coordinate systems. It's still the same point. Y and x hat represent the same point, just expressed in different coordinate systems. While u transpose x and x are different points. X is the original point. U transpose x is the projected point expressed in the frame defined by u, which is point y. And then x hat is the same projected point, but expressed again with coordinates in the original Cartesian axis. So it's the same projected point, but this time we express its coordinates in the original axis. Questions? No questions. Okay, is it a bit clear what we are doing? Okay, let's hope it is. Otherwise, I suggest you revise, you go back to first year course. You should have done at least a bit of this. But maybe you did it a few years ago, so you may need to revise it. Or in any case, these are the only two things that we will need: to project and to represent the projection in the original frame or in the frame defined by the projection matrix. So we said that to project a point, we define a matrix of basis vector that represents the Cartesian axis of the space where we want to project our point on. Then u transpose x corresponds to the coordinates of this point in the new Cartesian coordinate axis, in the new Cartesian plot defined by these vectors. These vectors will be the axis of the new coordinate systems. And then we have seen that we can represent the projected point in the original coordinate systems by simply multiplying by the same matrix U the coordinates of the projected point in the new coordinate system. From the new to the old coordinate systems, we go multiplying a sample by U. So if we have a point expressed in the new coordinate systems, uy gives me the coordinate of the point in the old coordinate systems. If we have a point in the old coordinate system, u transpose x will represent the coordinate of the projected point, and here I use projected because u is not full rank, so when I go in this direction, I may lose information because the new coordinate axis may not span the entire subspace, as we see here. The new coordinate axis do not have a direction to represent displacements along these kind of displacements. So the projection may lose information, the reconstruction, on the other hand, does not, because it just expressed the coordinates, the new point, the projected point in the old coordinate systems. Now, we can even show that if u is full rank, then also the first term, the first part, does not lose information, so these two would actually provide a transformation of the data in two different coordinate systems. So we would represent the same x here in the coordinate system defined by u, and vice versa. If we have a point defined in the u system, we can compute its coordinates in the original system as x. Notice that if I apply the reconstruction in this case, and u is full rank, what I get is this. But if u is full rank, since it's orthogonal, u transpose is equal to the identity, only if u is full rank. Full rank means that it's square, size n times n, and that's enough because since it's a set of basis vector, that's enough. Combined with the fact that it contains a basis of the space, that's enough to say that it's orthogonal. So in this case, this is exactly equal to x. And it's interesting to note that if u is full rank, and I apply the transformation, I can see the transformation as a change of coordinates, but something interesting happens if I take the new coordinates and I represent them and I use them to compute as if they were coordinates of samples in the original space. What does it mean? It means that let's imagine that we have a set of points like this in the original space. Let's imagine we use a full rank u, so we just compute the coordinates of this space over the new axis defined by these two directions. The coordinates of these points, if I look at them from the point of view of the new frame, would look like what? They would look like points that are here. So if I compute these 3 points, I get the coordinates of the points in the new reference frame. Now let's do something that may look weird, but let's treat these points as if these were coordinates of new points in the original frame. So let's take these y's and treat them as coordinates of new points in the original frame. What do I get? I get that these points would be somewhere like here. If I take these points as coordinates of points in the original space, they will look as points that behave here. What happens? Well, if I look at my original points and at the new points, I can see that the new points behave as if they were a rotated version of my original points. What does it mean? It means that we can consider the transformation y equal u transpose x as a projection, or in the case where, in general case, let's imagine u is full rank, because otherwise we're losing information. But if u is full rank, we can imagine that u transpose x corresponds to a change of basis. So we have seen in which sense we can interpret this as a change of basis. It's a representation of x in the new frame defined by u. But the same operation, if I assume that it's applied to points that then, to give me coordinates of new points starting from coordinates of the original points, corresponds to a rotation of the original points. So if I interpret these as coordinates of the point in a new reference frame, then what we said holds. But if I interpret these values as the coordinates of new points in the original frame, this would correspond to a rotation of the original samples. So multiplying data by an orthogonal matrix can be interpreted as in two ways. In a way, we are representing points in a new frame, or we are computing new points that corresponds to a rotation of the original samples in the original frame that we were using. Now, this second interpretation we will not need a lot, but it's important when we want to see what happens in practice when we will use it to show something that happens when we apply this kind of transformation to our dataset. So remember that when U is full rank, I can interpret this process as computing coordinates of the original point in a new reference frame, and then these are coordinates of the same points in the new frame. But if I interpret, on the other hand, the output of that operation, Y, as new samples, as transformed samples in the as coordinate of points in the original reference frame, this operation will give me points that are a rotated version of the original space. Which is the rotation? The rotation is the opposite of the rotation that would bring the original Cartesian axis on top of the new frame axis. So if to align the original axis to the new axis, I need to perform the rotation. When I interpret this kind of rotation, when I interpret these points as coordinates of the samples in the original space, the points that I get would look like the opposite rotation of the original points. Okay. Let's see. Now, the last step we need to perform our dimensionality reduction is to see how to use this to compute a projection of our data that preserves the information. And I say we do this after another 10 minutes break. Okay. Last one, please close the door. Okay, we have spent some time defining what is a projection, how we project a point in a new subspace. We didn't say it, but we are working with subspaces, so we have a new Cartesian axis, but the origin of the space is the same as the origin of the initial space. So when we talk about subspaces, we consider surfaces or, well, planes, lines, spaces, but what's important is that they all contain the origin of the original space. So here the origin is preserved. Here when I was going from 2 dimension to 1, the origin was contained also in the subspace. The subspace is the set of points defined by my basis, in this case this line. So I didn't say it, but the word subspace means that the origin is part of those points that get preserved. So the origin is inside both the original and the new space. Why this is important? Because, for example, I may ask myself whether should I project a point over this u-axis, but I can also decide I project the point over the line defined by this equation. I can represent a surface that in 1 dimension corresponds to a line, and I can say, okay, let's project my x rather than on a new subspace on this surface. We are not going to do this. We are going to work with subspaces, so all our projection directions will pass through the origin. Now, this may be interesting for our task. We will see that we actually don't need to treat it explicitly. Okay, so our goal is to go from a n-dimensional space to an m-dimensional space. Now, here we consider a zero mean dataset, but actually we don't really need to make this assumption here at this moment. Maybe what we say will actually work for any dataset with some issues that we will discuss if the dataset is not centered. So this is not really an assumption that we need for what we are going to discuss. The idea here is we want to find a subspace that preserves the information. We see that if the dataset is non-zero mean, then finding a subspace may lead us to something that is not that interesting, at least for some of the directions that we take. So we will generalize the problem to finding a surface rather than a subspace over which to project. We will see at the end of the lecture that finding a generic surface will correspond to finding a subspace over a centered version of our data. So for this reason here, we were assuming zero mean dataset, because in the end, if the dataset is non-zero mean, we will still transform it so that it becomes zero mean. But to be precise, for what we develop now, we don't need to make this distinction yet. So we have a dataset, and we want to find a subspace that is a surface that goes through the origin over which we want to project our data. We said already that we can represent a subspace by a matrix whose columns are orthogonal. The columns of the matrix represent the basis of the new space. We call this now matrix P because it's the PCA matrix and it's a projection. So there are these two reasons to call it P. Matrix P will be made of columns. How? These are column vectors. Each column vector is n-dimensional, so it has a size equal to the input size. And I have m column vectors because this represents an m-dimensional subspace. So these are the vectors, the unit vectors that represents the axis of the subspace where I want to project my points. The vectors are orthonormal. It means that this holds, well, actually this holds for any I, while if I take two different vectors, their product is zero, exactly as we have said before. We have seen before how we can define the projection of a point X on the subspace defined by P. It's nothing else than P transpose X. So if I have X and I project it in this way, I get the coordinates of the projected point in the new reference frame. And we can compute the reconstruction by simply taking Y and pre-multiplying it by matrix P. This is nothing else than what we said before the break with P replacing matrix U. Now, the problem is we don't know a good matrix P, so we want P is a bond. We have a model. We have a parametric model. The model is we use projection in a subspace. It's parametric. The subspace that we choose is defined by a matrix P that contains parameters. The size of P does not depend on the input data, so it's a parametric model. The problem is we need to find a way to estimate a good value for matrix P. How do we get a good value for P? Well, the value for P that we want to find depends on what is our task. We said that for the moment we look for a way to compress information in such a way that we minimize the loss of information. So we need a way to quantify what we mean by loss of information. Now, depending on the task, there may be different ways to do that. For example, we discussed before the break. If I'm working with audio signals, then loss of information may be interpreted in the sense of loss of information that can be understood by the human ear. The same for images. Compressing an image, loss of information means loss of information that allows a human to tell apart two pictures. If two pictures for the human looks the same, then from the point of view of the task, I didn't lose information because what the human perceives is exactly the same thing, even though I may have lost information in terms of bits of information. So I may not be able to reconcile perfectly the original image, but from the point of view of somebody who looks at the picture, he will not see differences. That's a good compression. Now, how we define something that is general? Well, unfortunately, we can't define something that works for every task. The way we follow here is we define similarity in terms of Euclidean distances in the original frame. So we use the concept of distance between points to define whether two points are similar or not. Points that in the original frame are close will be considered similar. So these 2 points will be similar, while these 2 points will be considered different because they are far away. So if points are close, they are considered similar. If points are far, they are considered different. Now, we don't need to specify how much far to consider them different. It's just relative. The farther 2 points are, the more they differ. The closer 2 points are, the more they are similar. We can therefore take our training set and for each sample compute what is called the reconstruction error. That is, we project our point, we represent the projection in the original frame because we need to have its coordinates in the original frame. Once we have the coordinates in the original frame, we can compute the distance between the projection and the original point. The farther the original point from its reconstruction, the higher the difference between the 2 points. We measure this in terms, in this case, for PCA, we measure it in terms of Euclidean distance, and in particular, squared Euclidean distance. The squared Euclidean distance is called the reconstruction error. The larger the distance, the larger also the square Euclidean distance, the larger the square Euclidean distance, the worse is my reconstruction. With a reconstruction that becomes quadratic, grows the goodness of my reconstruction becomes quadratically worse as I move far away the original and the reconstructed point. So if points are close, my error will be low. If points are far, my error will become larger and will grow in a quadratic way. Similar to the mean square error that you have seen maybe in regression problems. Just that there you had a target variable that you wanted to be as close as possible to your label. Well, in that case it was a continuous label. In this case we have a sample and its own reconstruction. Now, how do I measure the reconstruction error? Well, I can't know what is the reconstruction error for points that I have not seen, but I have my training set. What I can do is try to look for a solution that is able to at least minimize the reconstruction error on my training set. So I will compute the reconstruction error on my training set, and in this case, the simple way I can compute it is considering all samples, summing over all samples, that gives me the reconstruction error. Or if I want, I can take an average of the reconstruction error, which is just the sum divided by the number of samples. We will see that whether I take average or sum, it will not change. So whether you put the 1 over k here is irrelevant for the rest of for our solution. But let's put it there because it's easier. Well, because it becomes nicer afterwards. So we have average reconstruction error to minimize. The average reconstruction error, if we write it properly, is a function of what? The data and the parameters of the model. Here I just replaced each point, each xi hat, each reconstruction expressed in terms of the original point. Projection followed by back projection. So this is a function where p are the parameters and all the rest of the quantities are known. Xi's are the samples in my training set, so they are given, they are numbers. I can put their numbers, and if I give you a matrix P, you can compute a quantity that corresponds to the reconstruction error for that matrix. Our goal is to find the matrix P that gives the best reconstruction error. Optimization problem. We find the model parameters by minimizing a suitable objective function. In this case, suitable is we want to minimize the average reconstruction error defined as the average square distance between original and reconstructed point. Now, this is a constraint problem because we said that we want P to represent a subspace. So this is a constraint problem. We want to minimize that function subject to the fact that the columns of P must be also normal, which means that we can express it in matrix form, what we wrote before. We have that Pi transpose Pj must be equal to 1 if I is equal to j, or 0 otherwise. In matrix form, we can encode all those information for all I and j by saying that P transpose P must be equal to the identity. Remember that P transpose P is the matrix multiplication between these two matrices. If I have 3 arrays, so here I have P1 transpose P1, here I have P1 transpose P2, P1 transpose P3, and so on. So here I must have 1, and outside the diagonal I must have 0. So that's exactly the same thing. So goal, find the minimizer of this expression with respect to P. Solution, well, solution requires doing some manipulation of this expression. Manipulation of this expression that are of interest, but we are maybe a bit late. No, we are not that late. But I will go quickly in any case, because what matters here is more the results. I just want you to show a couple of tricks because we will need them, we'll find them repeatedly. But how do we solve this? We have an objective function we want to minimize. We first observe that if we have a vector v, the square norm of v corresponds to the scalar product between v and itself, which we said we can express in this way. Which means that all these products, all this norm, can be written as this vector transpose the same vector. This is a vector because this is a vector, this is a vector, this is a vector, and the difference between the two is a vector. So this is a scalar product between two vectors. It's a norm, it's a square norm of a vector. Now I have a product between vectors. This is equivalent to xi transpose minus pp transpose xi transpose, all multiplied by xi minus pp transpose xi. When I have a transpose of a product, this is equal to transposing the single terms and inverting the order of the terms. So if I have A, B transpose, that's B transpose times A transpose. Rules of matrices. So I bring the transpose inside, then I have a product between vectors. When I have A, let's say A plus B times C, then it behaves like numbers. It's equal to AC plus BC, so plus B times C. This is a column vector in this is a row vector in our case, and this is a column vector. This since they are transposed, these are row vectors, while these are column vectors. So I can simply develop the product by computing the product of all the terms, of all combination of terms. What I get is this expression. In this expression, I can observe that since I'm optimizing with the constraint that P transpose P is the identity, as long as I keep that constraint, that means that I can take P transpose P to be the identity, so this term here disappears, this product here disappears because it's P transpose P. What I'm left with is this. Then actually observe that this is equal to this, so actually I remove this and I have 1 here instead of 2. Last trick that I use, I have xi transpose xi minus xi transpose P transpose xi. I use a trick that tells me that this is a scalar. Then, if I interpret this scalar, I can interpret this as, if I have a scalar 1.3, let's say, this is a scalar, but I can also interpret it as a matrix with 1 element, in NumPy notation, something like this. 1 times 1 matrix with 1 element, of which I take the trace. The trace of this matrix is exactly 1.3, okay? So I can interpret this as a matrix which I take the trace of. It's a 1 times 1 matrix. Then, properties that you may not know, but also about the trace of A, B is equal to the trace of B, A. So, when I have the trace is invariant to permutations, or a trace of a product is invariant to permutation of its elements. So, if I have A, B, C, this is trace of C, A, B. So, I can perform a rotation where the last element comes back in front. And it's invariant. This is a property of the trace. Which means that the trace of this can be written how? I move xi transpose on the other side, then I move also P on the other side, and I write it in this way. Why? Because now I realize that what I want is to minimize my function with respect to P. This is a sum of two terms. The first term doesn't depend on P. When I minimize a function, if I have a function of P that behaves like some values plus that doesn't depend on P plus some other thing that depends on P, the value of this term is irrelevant for minimization. I'm looking for the minimum of function. This is just translating my function. This is F, this is G. They differ by a value V, but that doesn't matter. The minimizer will always be in the same position. So whenever I have additive terms that do not depend on the parameters, I can just throw them away. And this is something we will do a lot. In machine learning, you don't have no idea of how many terms that you just don't care about are in the equation, that if you were to keep all of them every time, you would just be wasting half of the space just to write irrelevant terms. So get used to irrelevant terms disappearing. This term is irrelevant for the task. We maximize with respect to P. So we don't care what that value is. What we care is that we essentially want to find the minimizer of this. So the minimizer of the original function is the minimizer of this expression. The minimizer of this expression can be obtained by looking what? If this is the function that I want to minimize, I can alternatively maximize minus that expression. So if I have this function, imagine that that is a function of the parameters P, and I change its sign, then the minimizer of the original function will be the maximizer or minus the function. The minimizer, let's say arg min, so the minimizer over P of a function of P is the maximizer over P of minus the function. We are flipping the sign. Whatever was the maximum of the function or the minimum of the original function becomes minus the maximum of the minus that function, but the position of the minimizer becomes just the position of the maximizer. This is F, and this is minus F. And this is P, of course. So we can solve our problem by actually looking for the maximization, one more step, of this function. Then trace is a linear. Trace is nothing else than a summation. We have a summation here over samples. We have a summation here over the elements of the diagonal of this matrix. Remember that the trace of a matrix is just the sum of the elements on its diagonal. So trace is nothing else than summing these values. We can exchange the two. We can bring the trace outside and the summation inside the trace. This gives me trace of sum over I of P transpose xi, xi transpose P. I have a summation. This P does not depend on I. It's multiplying the rest, so I can bring it outside the sum. This second P does not depend on I, so I can bring it outside the sum on the right. What I get is P transpose sum over I of xi, xi transpose, again multiplied by P. 1 over k. Why this is important? It's not important because now we know how to solve this, but it's important because it highlights that our solution depends on this quantity taken from the data. This quantity, we don't give it a name, but we will see that if our data are zero mean, corresponds to what is called a covariance matrix of the data. This is true only if the data is centered. We will see that when we extend the model to deal with, to find a generic surface, we will get a similar solution where this will be the real empirical covariance of the data. We will see that in a moment. So it's important to have to highlight that this is what the problem depends on. Let's call this matrix C. We have to maximize this matrix with respect to P, subject to P transpose P equal the identity. This is how the problem depends on the data. Depends on the data through that matrix. We don't prove it. We can show that if this is the matrix C computed from the data, the solution to P corresponds to taking this matrix C, computing its eigenvectors and eigenvalues. That is, we will do it by computing the eigenvector decomposition of the matrix, and then the solution for P will correspond to the first M eigenvectors corresponding to the M largest eigenvalues of matrix C. This matrix C, as I said, if the data is centered, is the empirical covariance matrix of the data. If it's not centered, it's not, but we will see that in that case, we will generalize the model with something that again computes the correct data matrix. So the solution depends on this matrix. How? We can show, and I'm not going to do it, that if I take the M leading eigenvectors of this matrix, leading eigenvectors are the eigenvectors corresponding to the highest eigenvalues, then what I get is exactly the matrix P that meets this constraint. The eigenvectors form a basis. So if I take M eigenvectors, I get orthonormal columns for M and for P, and these eigenvectors will give me the maximum of that function. They will provide the direction that minimizes the reconstruction error. So how do we compute it? Typically, we will compute the eigen decomposition. That's why we were interested in the eigen decomposition at the beginning. We eigen decompose our matrix C, and then the M. First, then we sort our eigenvectors by descending order of the eigenvalues. Then the first M eigenvectors will correspond to the matrix P that we are looking for. Now, we need to pay some attention to what happens if we apply this problem to data sets that are non-zero mean. We said we don't need to assume the data is centered, but if we apply this approach to data that is non-centered, what happens is that typically the first leading eigenvector will somewhat point towards the mean of the data. Not necessarily exactly the mean, so it will not necessarily be the line that connects the origin with the mean of the data, but it will be close to that orientation. Why? Again, it's something that we take as true because we don't have time to prove it, but maybe I will say a couple of words when we see what are the characteristics of the directions that we find that may explain why we have this behavior. In an intuitive way, you can imagine that if I have to have a direction, remember that I need to project over a direction, my direction must pass through the origin. So if my points are very far from the origin, you can imagine that any direction that does not point towards my samples will have a large reconstruction error. So if my data are here, you can see that to have small reconstruction error, I need to consider only directions that are somehow aligned towards the dataset mean. Any other direction that I may consider will have a huge reconstruction error when I project my samples over that direction. So in this case, it's difficult to show because we need more than two directions to show this, but this will typically affect the main direction that we find. That is, the first principal direction, the first direction of P, will typically point towards the dataset. The other directions will, in general, be fairly good, so it's not a big issue on its own, but still we are wasting some directions to represent something that typically is non-informative. What does it mean? It means that in most cases, the origin of the feature space is somehow arbitrary. It just defines how we represent our points, but typically, in most cases, if we change the origin of our space, and of course we compute the coordinates of the samples in the new space, we don't lose any information about the task at hand. So typically, it's like saying the origin of the space is somehow arbitrary. Imagine I'm measuring the height of a population to perform a classification problem. I know that males are taller than females, so I will use this information to build the histograms of the two populations. Whether I put my origin as 0, 8, or the origin of my axis as 100 centimeters, and then here represent only what is left over 100, it will not change the information that is there. The information that I care about is the relative height between male and female. So the difference between the heights of males with respect to females, not where I start measuring the heights. If I start measuring at 0 or somewhere else. So typically, the origin of the space is not particularly interesting, which means that we have no reason to decide that we want to have a subspace that should preserve the origin. We may say, okay, we don't care about the origin, let's look for a generic surface which allows us to avoid this, because in any case we don't care that it doesn't pass through the origin. Now this is a bit more complex. A possible way to do it is to look for a generic projection surface, which is not necessarily a subspace, but casting the problem is a bit more complex. A way to cast the problem, and again, we just say it without proving, we can cast the problem as how? Well, we can cast the problem of finding a generic surface as what? As finding a shift of the data so that I can consider the new surface as if it was a subspace of a new reference frame which has its origin shifted with respect to the origin of the original frame. So rather than looking for a subspace as we did originally, we look for a surface, but instead of looking for a surface, instead of representing this surface as an equation in the original frame, we do an opposite thing. We say, okay, let's move these points somewhere around. Let's assume that we can move these points somewhere. Let's still look for a direction that goes through the origin of the subspace, but considering a shifted version of the data. Notice that shifting data, I can see shifting data as taking my points and moving somewhere else, but I can also interpret shifting data as doing what? As taking my reference frame and put it, my new frame, new coordinates, somewhere else inside the points. It's the opposite shift. I can see a translation of the points, a movement by A, as I shift the points by vector A, or as a shift of the frame that represents the coordinates of the points in the direction that is opposite to A. In this sense, I can cast the problem of looking for a surface as casting the problem of looking for the origin of a new space, followed by plus looking for a direction that goes to the origin of this new space. But this can be represented as looking for a shift of the data in the original frame, plus looking for a subspace. Essentially, we want to look for a shift such that then when we apply our projection over the shifted data, we minimize the reconstruction error. The optimal solution for this shift corresponds, we can show, to the dataset mean. So if our data is non-centered and we want to find an optimal surface, the way we can operate is we consider a shift of the data that centers the data with respect to our coordinates. What does it mean? It means that we can interpret this as we move the data so that it's centered around the origin of the space, or if you prefer, we move our coordinate systems so that it's centered on the position that the data had originally. These are two interpretations of the same operation. In both cases, at the end, I will end up with a coordinate system where the points look centered around the origin of the coordinate system. So this is the optimal for the mean. For the direction, we already know that if the direction goes through the center, the optimal solution corresponds to the principal eigenvectors of the matrix computed by the shifted data. But the shifted points are what? Well, the shift operation will transform each point into the point minus the mean. So these will be the points for which I will compute the PCA solution. So first step, each sample is recentered, and then on the centered samples, I compute the PCA solution. If I compute, let's call this X prime. If I compute the matrix C over the samples X prime, what I get is that I can express the matrix C in terms of the original dataset samples as the sum of each xi minus the mean of the dataset times the same vector minus the mean of the dataset transposed. These are the samples over which I apply PCA, which means that the solution for the PCA subspace corresponds to the leading eigenvectors of this matrix. This matrix is what is called empirical covariance matrix of my dataset. It's the matrix that corresponds to a covariance matrix computed over data. So taking the data as if they were an empirical distribution, they would be the corresponding covariance matrix. It's a quantity that represents how spread are the points along the different directions. How? Well, the fact that the solution are the eigenvectors of the covariance matrix tell us something about what PCA is actually doing. Let's see, we'll come back to this slide in a moment, but let's see what PCA is doing if I apply the PCA projection following using the eigenvector decomposition that I said before. we need to compute the covariance matrix. The covariance matrix of the data will give us the directions over which to project our samples. First step, we compute the eigendecomposition of the covariance matrix. We get matrix U and diagonal matrix U of eigenvectors and diagonal matrix of eigenvalues, sorted by decreasing values of the eigenvalues. Now, we said that when we apply PCA, what we do is, in this case, we will take our test sample, center it as well, because we are working with centered version of the sample, so the same centering should be applied also to any data that we want to project, and then we project over P. Now, let's imagine that rather than using P, for the moment, we don't select a subspace of dimension M, but we keep all the set of eigenvectors. Remember that P contains the first M columns of U. So now let's consider using all the columns of U. What happens if I compute my projected samples? So I apply U transpose X, and again, I assume that the data is centered, otherwise I will need to center my samples. What happens if I apply the transformation U transpose these transformations to all my samples? If I apply this transformation to all my samples, and again, let's assume they are centered for the following so that I don't have to write minus X mean every time, what happens to my data? Well, we said that multiplying by a full rank orthogonal matrix corresponds to a rotation. Which kind of rotation? Well, let's look what happens to the covariance matrix of the transformed samples when I apply the transformation. Remember, my data is centered, so my new points are these. The covariance matrix for the new points is defined as the outer product of these values by themselves, and I don't need to remove the mean because the data are centered. So this is what I would compute as covariance matrix for the transformed samples. So if I were to compute my Y and then compute the covariance matrix, this is what I would obtain. I bring the U outside of this summation. So the summation is applied only to the terms inside this red parenthesis. I get this expression. Why? This is inside this matrix C, which is decomposed as U sigma U transpose. U and sigma are the decomposition of C. So I can represent C in this way. When I write everything, I realize that these two terms simplify because it's the identity, and the same happens to these two terms. Result, the covariance matrix that I obtain for the transformed features is diagonal. What does it mean? It means that if I multiply by U transpose, I transform the data so that what are called the principal direction of the covariance matrix become aligned with the Cartesian axis. What are the principal directions of the covariance matrix? We will see why, but we can represent the covariance matrix as ellipses. These ellipses has directions. The principal directions corresponds to orthogonal direction that give us what? The first direction is the direction where the variance is maximum. Then the second direction is the first direction that is orthogonal to the first one, over which the residual variance is maximum, and so on. So they are orthogonal directions oriented in such a way that the first gives us the direction with maximal variance, the second one gives direction with the second maximum variance, and so on. How can we see this? Well, when we apply U and we align the direction of these ellipses to the axis of the Cartesian, to our Cartesian axis, we get a diagonal matrix for the variance. So the elements of this matrix represent exactly the variance along these directions. And the eigenvalues of sigma are sorted. So the first component will have the highest variance. The second component will have the second highest variance. Each of these elements corresponds to the variance along the corresponding principal direction, or along the corresponding variance direction, if you prefer. Multiplication by U transpose would simply correspond, if I see it as a rotation of the samples, to rotating my data in such a way that the covariance matrix principal axis become aligned with the Cartesian axis of my original space. So that now the direction of maximum variance will be the coordinate 0 in my vectors. So this coordinate will now contain the elements of, let's say like this, U1 transpose X will be the coordinate that contains the direction with maximum variance, and so on. So here. Now, one last thing that is not in the slide. If I do this rotation, how can I represent my PCR projection? Remember that the PCR projection means take P transpose Xi, and in this case we want to say we have non-centered data, we will need to center it. But P is just the first M columns of U. So I can see the PCR projection is doing what? Well, I can take U transpose X. U transpose X will contain what? Well, minus the mean, of course. But let's assume the mean is 0, so I will not write it now. The first column of U transpose X, second column of U transpose X, mth column of U transpose X, and then all the other columns of U. So if I apply this operation, I get a vector that corresponds to this. If I truncate my vector here and I remove these components, I just throw them away, I have exactly the PCA solution. This is P transpose X. So I can interpret the PCA as doing what? I take the covariance matrix of the data, I rotate my data so as to align the directions of the covariance matrix to the principal axis, and then I throw away all the components that have lowest variance, which will be in the lowest part of the new data that I obtained. The rotated data will have its coordinates sorted by decreasing variance of the data. The directions will be aligned to the principal direction of the covariance matrix. PCA will select the direction with highest variance in my data, represented in a way where the covariance matrix of the output space is aligned with the Cartesian axis directly. Questions? Anybody alive yet, still? Okay, meditate on this. Practical considerations for today, and then we stop. We said the way we apply data is we apply it directly to centered data. So typically, we will start computing the dataset mean, then we will center all the data, both the training data and, if we need, evaluation data. They will also be need to center in this way. We are moving our coordinate system so that it corresponds, the origin of the coordinate system corresponds to the mean of the training set. Training is important, not the mean of the data, but the mean of the training data. So we need to apply this transformation to all the samples that we work with, where this X, however, is computed from the train set mean. So this is the train set mean, and then this mean will be used for any data that we want to project, but we will not re-estimate if we change the data set. It will always be the training set mean. So first step, we center our data, then we compute the covariance matrix that, in terms of the original samples, is going to be written in this way. If our data are centered, then we can compute in this way because the mean is 0. If I recompute the mean using the Z transformed data, the mean of the Z transformed data is 0. So to be precise, here I would have to put Zi minus mean of Zi, so Zi minus the mean of Z, but the mean of the training set computed in Z is 0 because we transform the data so that it has 0 mean. So we don't write it anymore. We compute the eigendecomposition. Typically, what we do is we compute either from this or from this. That doesn't matter how you compute C. Then you compute the decomposition of C. Then you take the first M column of C and use them for the projection. Any point that you want to project, we start from the original point, will be centered around the new axis for which the P matrix is optimal, and then we will project over P. Notice that in this case, if you want to reconstruct the original Xi, we need to reconstruct the original Xi by taking Y and multiplying by P. I don't know whether there is a bar over P here. But then, this is the value of the reconstructed point in the Cartesian axis that has the origin corresponding to the mean of the dataset. If we want to represent the point in the original frame, so the one where the data were not centered, we still need to add back the mean that we removed from the data. So depending on what we want to achieve, this we may not need. We may want to do just this. We don't care to reconstruct, to reshift back also the origin of the space. We may want just to compute the reconstruction of the shifted data. We may want to compute the real reconstruction, which in this case requires removing the mean. Sometimes we don't even apply this anymore. That is, we find P by solving this problem, but then you may see people doing just this. We project the sample Xi over P without centering the samples again. What is this? Why we can do this? Well, because we will see that for many problems, we don't really care whether the output is centered. And in any case, remember that if I want to compute this, and I have this value for the training set, remember the B transpose X mean is equal to what? Is equal to the mean of the elements Y. So if I try to project all my samples without recentering them, I can always recenter the projected sample and obtain the same thing that I would have obtained if I had centered the original data. Projection is a linear transformation. The mean would not change. So whether I first shift the data and then I project, or if I first project and then shift using the projected mean, would not change the result. We will try to avoid these kind of things, but these is things that you may find. You may find people that compute the PCI projection, compute the covariance matrix in this way, then you apply PCI and you don't remove the mean. Why? Because the algorithm that you apply afterwards will take care of the mean in any way, in some way that makes sense for that algorithm. So you don't care here that you remove the mean, because in any case it will be taken care by some other step to do the proper thing. So in some cases you don't do useless steps when you know that they are useless. So what you see here is the pipeline, the full pipeline, but in some cases you may see many variations of this, which makes sense depending on what you're going to do with the data that afterwards. Okay, I think we can stop here. Next week we will start using PCA in the laboratory, and we will also see briefly the effects of PCA, and then we will move to LDA. Okay, I would say let's make 10 minutes break for those who have squad now. I will start the squad laboratory in 10 minutes. And for those at home, for practical purposes, I will close the virtual class and I will open a new one for the squad. So you will be disconnected and you can reconnect to the next one.